Hello everyone. So in this video we are going to look at one of the questions that has been asked in the interview for the post of scientist engineer at Indian Space Research Organization. So the question was basically from the subject of strength of materials and more specifically from the chapter of torsion. So the question goes something like this. So they have given two shafts. Let me draw them for you. Okay. So this is a solid shaft with a diameter of d subscript s, and another shaft was a hollow one. Okay, so whose inner diameter is given by dhi and the outer diameter is dho, and the condition given was both the shafts have their outer diameter equal to each other. This is the condition. Now as a design engineer, if you have to use one among the two shafts, which one would it be, provided it is going to be used for some spacecraft application? Okay, now in order to make this decision you have to find the torsional shear stresses for the two shafts, and based on that you can arrive at the final choice, right? So I know that most of you have already come across this particular case where the outer diameter of the two shafts are equal, and you easily come up with the conclusion that in this case, when the outer diameter is a constraint, then solid shaft is a better choice. Okay, so let's see whether that thing is the so let's see whether this is the correct answer or not. So what I have to do is, first I need to find the torsional shear stress for both of these shafts. So we need to find an expression for the torsional shear stress which comes from the torsion equation. So I'll just write the torsion equation, which is tau by r, t by j, and g theta by l. So I'm going to equate these two things. So I get an expression for the torsional shear stress. So if I'm writing it for the solid shaft, the final expression comes out to be 16t by pi ds cubed, and for the hollow shaft it is 16t by pi d outer cubed into 1 minus k power 4, where k is equals to dhi divided by dho. Okay, now if we take the ratio of the two, what we get is this. So we might want to think from the value of k in order to arrive at what would be the stress in case of these two shafts. This value for k is going to be greater than 1, so the denominator is less than 1. So ultimately we directly conclude that in case of so we conclude that in case of hollow shaft the stresses are going to be higher provided the outer diameters are the same. And another case that we make for the two shafts are like when the weights are equal. So in that case, and the space is not a constraint, we conclude something like the hollow shaft will have a higher strength. In this case it is not completely true. Let me tell you why. So let's draw the variation of this tau h by tau s with respect to k. Okay, so in case of k equals to 0, the two shafts would be identical and the stresses would be the same. So this ratio is going to become equals to 1. So it will start at 1. So as we start to increase the value of k, what will happen is it will have this kind of a variation. Okay, and till a value of somewhere around 0.2, you don't actually see much of a difference in the value of the torsional shear stresses for the two cases. Okay, it's almost negligible. So what we can conclude from this variation is that even after the removal of you know 0.2, it's a ratio of diameter, right? So if I want to calculate the area, so 0.2 into 0.2 is basically 0.04. That's not a lot. So what we can say from the variation that we are looking at is that even after the removal of some material, okay, basically what k represents the ratio of the inner to the outer diameter. So if I am making a hole, basically there is some material that I have removed. So even after the removal of material, the increase in the torsional shear stress for the case of hollow shaft is not considerable. It's like negligibly small. So it did not do much in terms of the increase much. So basically it did not do much in terms of an increase in the torsional shear stress, but rather it helped us to reduce the weight. And why is it so important? Because they have mentioned this condition that we are going to implement this shaft for the spacecraft application. So weight reduction is one of the primary concerns, and if you are able to even bring about just 3 to 4% reduction in the weight of any component, then you are doing remarkably well. So from the equation it is not very much clear at the first instance, and we directly try to conclude this particular fact, but things are not the same when you try to look at it graphically, and that is a much better way of understanding the things, right? So this equation is something which is very common and all of you know it, but when you are interviewed at some premier organization like ISRO, then you cannot just stick to that particular equation. You have to actually think not in terms of the equation, but also in you have to visualize the situation where whether there is a possibility or not. Like at the first instance you would not want to use a hollow shaft, but somebody would have thought like what is wrong with using a hollow shaft, and they started to look into it, and finally this is what they come up with, which is very interesting. So the only point that I'm trying to make here is things are going to be very simple. It will not be much difficult, but the way you have to think and arrive at some answer is what will decide whether you're going to get selected in ISRO or not. Okay, so thank you for your time. I hope you have understood this concept, and this is how the approach needs to be.